Previously on Unknown Source, we delved into the fascinating world of quantum entanglement, a concept that has challenged and intrigued scientists for decades. We embarked on a journey into the realm of the infinitesimal, where the laws of physics as we know them begin to blur and the extraordinary takes the stage. We introduced you to quantum entanglement, a phenomenon that seems to defy our everyday logic. It's a concept that Einstein, Podolsky, and Rosen first brought to light in their 1935 paper, leading to the famed EPR paradox. It's this paradox that has been the seed for much debate and research in the field of quantum mechanics. We touched upon the notion of superposition, a characteristic unique to the quantum world. Imagine having a coin that's not just heads or tails, but both at the same time. That's superposition. It's only when we measure this coin, or in our case a quantum particle, that it chooses a state. We also discussed the peculiar correlation between entangled particles. These particles, once entangled, remain interconnected irrespective of the distance between them. Change the state of one, and the other responds instantaneously, as if aware of its partner's state. It's a connection that persists, challenging our classical understanding of causality and locality, but the story doesn't end there. As we venture deeper into the quantum realm, we'll explore more about the experiments that confirmed the existence of entanglement and its implications. So, gear up as we continue our journey, diving deeper into the astonishing phenomenon of quantum entanglement. We begin with physicist John Bell, whose theorem in 1964 posed that changes in one particle could instantaneously affect the other. This was a bold claim, one that rattled the foundations of classical physics. But how did Bell arrive at this theorem? Bell was fascinated by the idea of quantum entanglement, the peculiar interconnection between quantum particles that Albert Einstein famously referred to as spooky action at a distance. And so, he proposed a theorem to test this spooky phenomenon, a theorem that would become a cornerstone of quantum mechanics. Bell's theorem suggested that if quantum mechanics was correct, then the measurements of certain properties of two entangled particles would be more strongly correlated than could be explained by classical physics. In other words, there would be an entanglement that transcended the limits of space and time. But a theorem is only as good as its proof. And so, the scientific community set out to test Bell's daring proposition. Experiments were conducted with entangled photons, particles of light that had been linked in a state of quantum entanglement. These photons were then separated, and their polarizations, or the orientation of their waves, were measured. The results were striking. Despite being separated, the photons had matching polarizations more often than could be explained by chance or any classical theory. This was a clear demonstration of quantum entanglement and a validation of Bell's theorem. But the experiments didn't stop there. Over the years, researchers have continued to test and explore the limits of quantum entanglement, pushing the boundaries of our understanding of the quantum world. They have entangled not just photons, but atoms, molecules, and even larger systems, revealing the deep and pervasive nature of this quantum connection. These groundbreaking experiments not only confirmed Bell's theorem, but also opened up new avenues of research in quantum mechanics. They showed us that the quantum world is more interconnected than we could have ever imagined, with entanglement weaving a complex tapestry of quantum states. And as we continue to delve deeper into this quantum labyrinth, who knows what other wonders we might uncover. Quantum entanglement, as puzzling as it may be, has significant implications in today's world. As we delve deeper into the quantum realm, we find that this seemingly odd phenomenon can be harnessed for practical applications, some of which are already reshaping how we interact with the world around us. Take, for instance, the field of cryptography. In a world where information is the new gold, the security of our data has never been more paramount. Quantum entanglement offers a unique solution to this modern challenge. By leveraging the interconnected states of entangled particles, we can create encryption keys that are virtually impossible to crack. Any attempt at intercepting these keys would disrupt the delicate quantum state, alerting the parties involved and effectively preventing unauthorized access. In addition to secure communication, quantum entanglement plays a crucial role in the burgeoning field of quantum computing. In stark contrast to classical computers that process bits of information sequentially, quantum computers use quantum bits or qubits that can exist in multiple states simultaneously thanks to superposition. With entanglement, these qubits can be linked, allowing for an exponential increase in processing power. This could revolutionize areas like drug discovery, climate modeling, and financial optimization, where complex computations are required. Moreover, quantum entanglement is also being explored in the context of quantum radar. Theoretically, a radar system utilizing entangled photons could detect objects with greater accuracy and at greater distances than conventional radar systems, potentially transforming fields like aviation and defense. And let's not forget about quantum teleportation, the process of transferring quantum information over long distances. While it's not teleportation in the sci-fi sense, it does allow for the secure transfer of information, providing yet another layer of security in our increasingly connected world. While the practical applications of quantum entanglement are still being explored, its potential is undeniably vast and transformative. As we continue to unravel the mysteries of the quantum world, who knows what other incredible possibilities we might discover. Despite the confirmations and applications, quantum entanglement continues to spark significant debate and research. We're diving into a world where two particles are intimately linked, no matter how far apart they are. This spooky action at a distance, as Einstein famously put it, is a concept that has challenged our understanding of physics and the universe as we know it. One of the most intriguing aspects of this debate centers around the concept of hidden variables. The idea here is that if we knew more about these hidden variables, we could predict with certainty the outcome of quantum measurements. However, this concept has been refuted through Bell's theorem, which states that no physical theory of local hidden variables can ever reproduce all of the predictions of quantum mechanics. Opponents of the hidden variables theory argue that entanglement is not the result of any underlying mechanism or hidden factors. Instead, they propose that the quantum state is all there is, and when we measure a particle's state, we're not uncovering some pre-existing condition, but rather forcing the particle into that state at the moment of measurement. Yet, the debate doesn't end there. There are still theories and interpretations that challenge these views, such as the many worlds interpretation, which suggests that every quantum measurement causes the universe to split into multiple versions of itself. While the debates continue, one thing is clear: quantum entanglement has forever altered our understanding of the quantum world. This mysterious and fascinating phenomenon has opened up a new realm of possibilities, pushing the boundaries of our knowledge and challenging our perceptions of reality itself. And as we continue to explore, who knows what other astonishing discoveries await us in the quantum realm. As we stand at the edge of this quantum frontier, what does the future hold for quantum entanglement? As we gaze into the future, the possibilities of quantum entanglement seem as limitless as the universe itself. Given its potential for applications in communication, computation, and quantum radar, this field of study is becoming increasingly significant. Imagine a world where communication is not just secure, but practically unbreakable. Quantum entanglement could make this a reality. By harnessing the power of entangled particles, we could create cryptographic systems that are impervious to hacking. Information could be transferred over vast distances without fear of interception or disruption. This could revolutionize everything from military communications to online banking. In the realm of computation, quantum entanglement could pave the way for quantum computers, machines with processing power beyond anything we can currently fathom. By harnessing the power of entangled quantum states, these computers could perform calculations at speeds that would make our current technology look like an abacus in comparison. The possibilities for scientific research, data analysis, and artificial intelligence are truly mind-boggling. And let's not forget about many-body entangled systems. As we delve deeper into the study of these complex systems, we could discover new aspects of quantum physics that challenge our understanding of the universe. This could lead to breakthroughs in material science, energy production, and even our understanding of the fundamental nature of reality. But as with any frontier, there are challenges to overcome. The principles of quantum physics are notoriously difficult to reconcile with classical physics. Theoretical debates continue to rage, and practical applications, while promising, are still in their infancy. Yet, the potential rewards are too great to ignore. Researchers around the globe are dedicating their lives to understanding and harnessing the power of quantum entanglement. The journey through the quantum realm is far from over. Stay tuned, subscribe to Unknown Source, and join us as we continue to explore the wonders of the quantum world.